of this afternoon's short talk section, and the first speaker is Rak-Kyeong from Korea Institute of Advanced Study, and he's going to tell us Brane Bricks, UD 0.2 series, and toric Calabi-Yau.
Okay, thank you very much for the opportunity to give this talk here. My talk is based on Brane Bricks, 2D 0.2 series, and toric Calabi-Yau 4.4. And the talk is based on two papers. One was published in June, and it was in collaboration with Sebastian Franco from the University of New York, Kim and Sang-Min from Seoul National University, and then Yuko Yama, who is now at King's College London. And it's also based on the second paper, which was published last month in collaboration with Sebastian Franco and Sang-Min. So 2D theories have attracted a lot of attention recently from various different perspectives. If I give an example, if you think of 6D theories compactified on 4 manifolds, you obtain a large class of 2D 0.2 theories. And this class of 2D 0.2 theories, for instance, have to be studied by Rak-Kyeong over there and his collaborators. And they were able to find correspondences between 2D 0.2 theories, which they call triarities. So they were like generalizations of 4D silent polarities. In this talk, I want to talk about 2D 0.2 theories as all-volume theories of D1 planes. The transverse geometry of the D1 planes is the toric Calabi-Yau 4-fold. The toric Calabi-Yau 4-fold can be thought of as the target space of a sigma model that is defined through the 2D field theory on the D1 planes. In my talk, I want to talk about the T-dual picture of this plane construction. It's a type 2A plane configuration made out of D4 planes and NS5 planes. And this new type of plane configuration I want to introduce later is what we call a Brane Bricks model. And I will tell you later in my talk how the Calabi-Yau 4 data is encoded in the Brane Bricks model, and also vice versa, how from the Brane Bricks model I can read off the Calabi-Yau 4 data. So to start my talk, let me give you a quick overview of the 2D 0.2 multiplets. So I have a vector multiplet, a chiral multiplet, and a Fermi multiplet. The main purpose of this slide is basically that I have a special property here that the chirality condition of the Fermi multiplet can be deformed by a holomorphic function in terms of the chiral fields, which is called the E term interaction term. And this E holomorphic function carries the same quantum numbers as the corresponding Fermi multiplet. Later I will talk more about it, but for the moment you can see that the 2D 0.2 multiplets can be represented by a quiver diagram. The nodes are representing UNH groups. The arrows in the quiver diagram represent bi-fundamental chiral fields, and we represent by red lines the Fermi multiplets. So you can see that the chiral multiplets and Fermi multiplets carry quantum numbers for the gauge symmetry, which tell you how the lines and arrows are adjacent to the nodes in the quiver diagram. So I told you previously that the chirality condition of the Fermi multiplet can be deformed by a holomorphic function in terms of the chiral fields, which we call the E terms. But for every Fermi multiplet, I can have another holomorphic function associated to it, which is called the J term. So this J term is again a holomorphic function in terms of chiral fields, and it's a generalization of a superpotential. It acts as a superpotential term in the 2D 0.2 Lagrangian. So for every Fermi multiplet, I have two holomorphic functions associated with it, and they are called the E terms and J terms of my theory. So these holomorphic functions can be restricted to be monomial relations in terms of chiral fields. So in fact, this constraint we call the toric condition, and it severely constrains the class of 2D 0.2 theories we want to consider. So what do I mean by a monomial relation? So it's a relation, an equation, equality between two products of the chiral fields, and it can be graphically represented in terms of the quiver diagram as follows. If I pick a line corresponding to a Fermi multiplet, it is associated to two directed paths always, and these two directed paths are precisely these monomial products of chiral fields, which are identified to each other by either a E term or J term interaction term of minor order. Okay. In addition to this toric constraint, I have to make sure that gauge anomaly is cancelled completely. So the gauge anomaly contributions coming from the chiral and Fermi multiplets are shown here. In fact, all our gauge, so for the theories I want to consider, the gauge groups are all UN gauge groups, where all the ranks of the gauge groups are the same, set to be n. If I use that information, the gauge anomaly cancellation constraint simplifies to this very simple relation, which basically means that for every node, every gauge node in the quiver diagram, the number of chiral fields attached to that gauge node is larger than the number of Fermi fields attached to the gauge node by a difference of 2. Okay. So this sets a constraint on the set of quivers I can draw for the class of 2D 0,2 fields I want to consider. So here are some of the examples. For instance, this is a quiver diagram with two UN gauge groups with 4 Fermi multiplets, 4 fundamental chiral fields, and 2 adjoint chiral fields. And this quiver diagram is associated to a model which we call the conical MC model. If I look at a closer look at this example, the corresponding J terms turn out to be these cubic equations, and the corresponding E terms turn out to be these quadratic equations. And both J and E terms here satisfy the toric condition I told you about earlier. And because they are satisfying the toric condition, I can pick, as an example, two monomial products of chiral fields, and they will always correspond to two coupled paths in the toric diagram made out of chiral fields like this. If I successively pick pairs of monomial products, they will again correspond to different coupled paths in the toric diagram, in the quiver diagram. And then if I continue to pick these pairs of monomial products in the J and E terms, I can start to glue together the corresponding paths in the quiver diagram to obtain something which is intrinsically periodic on the free tools. It turns out that this diagram, this extended quiver diagram, is periodic on the free tools, and in fact you can think of this as the original quiver folded out by the J and E terms on the free tools. Okay, we call this extended periodic quiver diagram, this quiver diagram as the periodic quiver diagram of the 2D 0,2 field. The question is, where does this free torus come from? So I ended up having a free torus, and the free torus is encoded in the J and E terms and the quiver diagram, defining data of my 2D 0,2 field. And in order to answer that question, let me go back to the picture of D1 based on the Calabi-Yau fourfold. If I T-dualize this picture, I end up having NS5 planes having an holomorphic surface, and D4 planes which are suspended between these NS5 planes. The holomorphic surface on which the NS5 planes flat are parameterized by 3 complex coordinates, which I call x, y, and z. If I take the arguments of these 3 complex coordinates, they precisely parameterize the free torus I was talking about before. Let me go more into details about this holomorphic surface. In order to do so, let me have a look at the toric diagram of the Calabi-Yau fourfold. The toric diagram of the Calabi-Yau fourfold is expressed in terms of is associated with a Newton polynomial, which basically defines this holomorphic surface. If I take this Newton polynomial in terms of coordinates x, y, and z, and project this polynomial onto the arguments of the 3 coordinates x, y, and z, I obtain an object which, so the holomorphic surface in x, y, z basically asymptotes into planes on the free torus. If fact, these planes on the free torus have non-trivial winding numbers, and they are like, you can consider them as the boundaries of the holomorphic surface on the space of arguments of the free complex coordinates x, y, and z. For this particular example, which is the toric diagram, which is the tetrahedral toric diagram corresponding to C4, these planar asymptotic limits of the holomorphic surface are these 6 planes with different winding numbers to each other. Now you can look at these planes and imagine that these planes are all in the same free torus, and then you can guess that these planes will have non-trivial intersections. They will intersect on lines and points. In fact, if I introduce consistent orientations on these planes, point intersections of these asymptotic limits of the holomorphic surface can be oriented. And we claim that these orientations of point intersections of these phase boundaries correspond to chiral fields of my Hilbert diagram, like 0.2 hk. In fact, you can also have point intersections of these phase boundaries which are not oriented, and for these point intersections, we claim that these are mapped to Fermi multiplets of my 0.2. So you will end up having a set of phase boundaries coming from the holomorphic, from the Newton polynomial of my toric diagram, and these will intersect at the finite set of point intersections. And each of these point intersections are either oriented or not oriented, and they can be mapped to all of the chiral and Fermi multiplets of my 0.2 to the 0.2 quiver gauge field. By doing so, I reproduce the entire periodic quiver I was talking about earlier. In fact, I can summarize the entire combinatorial structure. I mean, I can summarize the entire phase boundary structure in terms of these complicated matrices. In fact, there's a lot of combinatorics involved. I just show you this slide because, in fact, the combinatorics of dealing with these phase boundaries can be used to express gauge. In fact, it can be used to generate gauge linear sigma model fields from the set of chiral fields having. I have no time to go through this, unfortunately, but I'm just showing you this slide because there's a lot of combinatorics involved to generate the sigma model out of this 2D theory. Now, what I want to mention in this talk is that now I have a class of 2D 0,2 theories, which are defined by the quiver diagram, the J and E term relations, and the toric diagram, and the phase boundaries that you can obtain from the asymptotic limits of the holomorphic surface you obtain from the toric diagram. And all these separate data points can be merged into a single graph, which we call as the Brane Bricks model. So a Brane Bricks model, we propose an object that uniquely defines the 2D 0,2 theory, and it's a tessellation of a free torus, and you can simply think of it as the dual graph of the periodic graph on the free torus I was talking about earlier. What is the special property of this Brane Bricks model? It's the tessellation of a free torus, and three-dimensional polytopes of this tessellation correspond to a gauge group in my 2D 0,2 theory. This polytope will be made out of even-sided faces. We claim that the dictionary here is that square faces of such polytopes correspond always to Fermi multiplets of my theory, and even other different sized even-sided faces of these polytopes correspond to chiral multiplets of my theory. The special thing here is that now I have also one-dimensional objects, which are the edges of the polygons and polytopes, and this three-dimensional tessellation. And these edges can be mapped to either a J or E term relation of my field. So we completely unify the data of J and E terms and the matter content of my theory in terms of a single tessellation of the free toes. In fact, more than that, this tessellation also encodes the holomorphic surface of my Calabi-Yau fourfold. So therefore, it also is a Brane construction. It can be interpreted as a T4 NS5 Brane construction. These surfaces can be mapped to the NS5 braids wrapping certain holomorphic surfaces on the free toes.
So maybe I missed. How is J dot E equals 0 imposed?
J dot E in this picture. In fact, I mean, well, that's a good question. In fact, it's probably imposed in the fact that this tessellation is closed. But I mean, yes, but we did. It's a condition you need to set as well. I mean, it's partially set because of the fact that I have monomial relations as J and E terms, and then if I use that, the J and E terms tend to go to 0 all the time. But yeah, that's a good question. How is that interpreted in this picture? And my guess at the moment is that the tessellation is closed on the free toes, and that sets the J and E terms. So let me give you an example. So I can now pick a random tessellation on a free toes. Let me pick one tessellation made out of octahedral prisms and cubes. And I map 2 of these octahedral prisms to 2 gauge groups of a theory. And I identify certain faces to be Chiral multiplets and certain red faces, to be Fermi multiplets. And here again, I have a cube. 4 faces are mapped to Chiral multiplets. 2 faces are mapped to Fermi multiplets. And I can continue to do that. I mean, the lines then from this map, from this dictionary, I can identify lines which are connected to these faces, and these lines correspond to monomial products of chiral fields. And in fact, if I collect the data of the tessellation, so this tessellation is precisely made out of these octahedral prisms and cubes, and given this this tessellation of the free toes, I can identify the gauge groups and chiral multiplets and Fermi multiplets and J and E terms using this dictionary. So you can now start to construct an infinite class of 2D 0,2 theories from the set of tessellations of free toes. In fact, an application I want to touch upon here is that you know that we can dimensionally reduce 4D n equals to 1 theories to 2D 2,2 theories. And these 2D 2,2 theories can be expressed in terms of 2,2 language. And in fact, 4D n equals to 1 theories corresponding to Calabi-Yau spaces have been studied extensively in terms of the 5 NS5 Brane constructions, which are known as Brane tilings by Hanani and collaborators. In fact, the procedure of dimensionally reducing this set of 4D n equals 1 theories to 2D 0,2 theories has a nice graphical interpretation. So here we are thinking of 4D n equals to 1 theory given by this bipartite graph on the 2 toes. This is an hexagonal tiling. And the dimensional reduction of the 4D n equals to 1 multiplets has a precise graphical interpretation of embedding the 2 torus into a free torus. So if I take a tessellation of a free torus and take arbitrary certain slice of that, certain 2 torus slice of that free torus line, I obtain a Brane tiling that describes a 4D n equals to 1. So there's a nice map. I cannot, unfortunately, I don't have much time to go through this, but the point here is that dimensional reduction has also graphical interpretation. So here I told you about periodic quivers, data coming from quiver and J terms, periodic quivers, Brane Bricks models, and Calabi-Yau fourfolds. All of them are united by this picture of the tessellation of the 3 torus. Now, in the for future purposes, we would like to answer questions like studies that have been made by 2D 0,2 fields in general. For instance, how is triality interpreted in terms of these Brane Bricks models? Can we compute elliptic genii of these 2D 0,2 theories? Can we identify new types of dualities, etc., etc.? So now we have a box of toys or tools to study the brane configurations of these phenomena in 2D 0,2.
Any quick question?
But do you think that the dualities, realities, and so on can be understood as movement? I mean, as I see. And
Well, yeah, so it's something, yeah, well, I cannot say much about it, but there was, so in 4D n equals to 1 theories, there was a brane constant. I was talking about brane timings, which are basically tessellations of NS5 and defined branes on the two towers. And cyber duality in 4D n equals to 1 was considered as a movement of NS5 branes. So this will be,
And also another thing, do you think that this geometrical understanding can help in classifying, for example, the possible 2,0 theory that you can construct?
Yeah, it's what's shown. Yeah, so any.
You are already able to classify.
Well, we have the language to classify. Okay. That's my point. I mean, you can pick any tessellation of the free towers and start to consistently apply the dictionary to identify the corresponding 2D 0,2 field. Yes.
And all the 2,0 theory can be constructed in this way.
Yes. But this is a very particular class of 2D 0,2 theories corresponding to toric Calabi-Yau form.
Yeah. Okay. Yeah.
Obviously, there will be, it's a subclass of all possible 2D theories.
Any further questions?
Your 0,2 is more frequent than have gravitational anomaly or
That
always cancel?
Yeah, we need to study that. But at the moment,